Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And today's lecture, I'll be discussing IGBT, its symbol, structure, input as well as output characteristics. IGBT, it is insulated gate bipolar transistor. And here is a symbol of IGBT, and it has got three terminals, namely gate, collector and emitter. And if you see MOSFET, it has got drain as well as source, whereas here in IGBT it is replaced with collector as well as emitter. And here the arrow direction is always faced towards emitter if at all, if it is N channel IGBT. N channel IGBT. We can make use of either P channel or N channel, but here in my lecture, I'll be throughout considering only N channel IGBT in order to avoid any sort of confusion. If it is P channel, in that case, this arrow mark will be away from the emitter terminal, and if it is N channel, the arrow mark will be facing towards the emitter terminal. And here, if you see, the voltage rating of BJT is 1200 volts, 800 amperes. And if you take the turn-off time of BJT is more. So that is the reason here BJT will be used in low frequency up till 20 kilohertz applications. And the advantage associated with the BJT is it has got low conduction losses. And if you consider MOSFET, it has got 500 volts. It can be used up to 500 volts and 140 amperes, whereas it can be applicable for high frequency applications because of its low turn-off time. And the disadvantage associated with MOSFET is high conduction losses. So here IGBT, it is comprised of advantages of both BJT as well as MOSFET. And if you see, the voltage rating of IGBT is 1200 volts and 500 amperes. And it can be used up to medium frequency applications, that is 50 kilohertz. And if you see, the turn-off time of the IGBT is from 0.25 to 20 microseconds. And these insulated gate bipolar transistors are compact, and it has got high input impedance similar to that of MOSFET. It has got high input impedance of about 10 to the power of 9 ohm, similar to that of MOSFET. So that is the reason the gate drive requirement is less. That means we can make use of simple electronic circuits as a gate drive. So the gate drive requirement will be less because of its high input impedance. And low on-state power loss will be there in BJT. So we can go for higher power requirement because of the low on-state power loss similar to that of BJT. That is the reason for IGBTs we can go for higher power requirement. We can meet high power requirements if we are making use of IGBT. So it has got both the advantages of MOSFET as well as IGBT, and this is free from secondary breakdown problem which was being there in BJT. And it has got moderate turn on and turn off time. So that is the reason we will be making use of this particular IGBT in medium power applications. So here medium power applications of we can make use of these IGBTs in DC motors as well as AC motor drives, in induction heating and static wire compensators, and UPS, uninterrupted power supply systems, and power supplies. We can make use of these IGBTs, but these are a bit more expensive when compared to that of BJT as well as MOSFET. Now, this is the MOSFET structure, and here if you see, this N type is connected to the negative terminal. And in order to understand the IGBT operation better, here I have considered the structure of MOSFET, and this drain terminal is connected to the N type, and positive drain is connected to the N type. In that case, when VGS is equal to 0, when particularly gate voltage is 0, and if drain to if VDD is applied and if negative is connected to N and this positive is connected to N plus region, in that case, see what happens, negative is connected to N, this will be forward biased. And here, since positive is connected to N, this will be reverse biased. And because this is reverse biased, there is no flow of current through the device. And you may ask me, what happens if we interchange these VDD terminals? This is positive and now this is negative. And if positive is connected to N, in that case, this will be reverse biased. And again, negative is connected to N, this will be forward biased. In either case, when gate voltage is 0, one of the layer is remaining reverse biased. Thereby, there is no conduction of current through the device. And what happens when we increase this VGS is equal to, say, for example, 2 volts. In that case, gate voltage is applied, and here this is the silicon oxide layer which is present, and due to the polarization effect, this particular silicon oxide, it starts acting as a capacitor and it starts storing the charge carriers. See, positive, because of the polarization effect, positive charge carriers are being applied on the upper plate and negative charge carriers are appeared or accumulated in this particular lower plate. So because of which previously there was no path for the conduction of the current, and now electrons are being accumulated here and it is creating a path, and thereby current starts flowing from source. Electron starts moving from source to drain, and current will be taking the reverse direction to that of the electron movement. So that is the only reason now drain current flows in the reverse direction to that of the electron flow. That is, drain current now starts flowing through drain to source. So this is the direction of the current. And in order to increase the current flow, we can increase this particular gate to source voltage now to 5 volts. In that case, the number of charge carriers accumulation increases. And because of which it creates a path for the electron movement. And because of which electrons will be flowing again from source to drain, and current will be flowing in the reverse direction to that of the first case. That is, current starts flowing from drain to source now. So this is how current conduction takes place in a normal MOSFET. And now let us consider, see, here there is the structure of the power MOSFET which we have considered, and this is a normal MOSFET, and this is the our required IGBT. And if you see, the IGBT structure will be just similar to that of the power MOSFET. The only thing is, here N plus region will be replaced with that of P plus region in the IGBT. And that is the only basic difference. And if you see, N minus region, this is common, and P body layer, this is also common, over which N plus region is being accumulated, and to which the emitter will be connected. And if you see, this injection layer, it is used to inject the charge carriers into the device. And if you see drift region, this determines the reverse blocking capability of the device. As the drift region, this is very important, as the drift region width is more, in that case it has got more capability to block the reverse biased voltage. This drift region determines the reverse blocking capability of a device. So that is the reason this drift region is very important, and this is N minus region. And if you see P plus substrate, the bottommost layer P plus substrate, it is connected to the collector terminal, and it is heavily doped of about 10 to the power of 19 per centimeter cube. And if you see, above which an N minus layer is present, which is common to that of the MOSFET. And here N minus layer is the drift region. As I told you, it determines the breakdown voltage of the device, and it is lightly doped, and it is in the order of 10 to the power of 14 per centimeter cube. Above which a P body layer is being accumulated, and it is in the range of, it is normally doped and it is 10 to the power of 16 centimeter, 10 to the power of 16 per centimeter cube, and above which this N minus layer is placed, and whose doping level it is heavily doped. N plus region, it is heavily doped, and it is 10 to the power of 19 per centimeter cube. And to this particular N plus region, emitter is being fixed. And now see, when emitter to collector is connected, in that case, P terminal is now connected to the positive terminal, and N terminal is connected to the negative terminal. And because of which, if you see, since P is connected to positive, this P plus layer will be now forward biased. And since N is connected to negative terminal, this N plus terminal will be forward biased. And this P layer, if you see, this P body layer is connected to negative again. So that is the reason this remains reverse biased. So these two junctions are forward biased and this junction is reverse biased. And due to which, if you see here, P plus layer, since it is connected to the positive terminal, when alike poles are connected, in that case, holes tries to repel away from the positive terminal. Holes try to repel away from the positive terminal. So holes will be injected into the, it will be injected towards the emitter layer. So that is the reason when the gate terminal, gate voltage is applied, and when emitter to collector voltage is applied, in that case, the current starts flowing from P plus layer to that of N plus layer. Again, here from P plus layer, the holes will be moving towards the emitter terminal, and that is the reason the current direction will be right from collector towards the emitter terminal. Current will be flowing in this direction. It is because if you see, P plus layer is forward bias as well as N plus layer is forward bias. Because P body is reverse bias, current will not flow through this particular layer. That is P body layer, the current doesn't flow, and current will be flowing right from collector towards that of the emitter, that is from P plus layer to N plus layer. That is the only reason we call this bottommost layer as injection layer, because it is injecting charge carriers towards the emitter. As I told you the reason, because P is connected to positive, it will be holes will be repelling away from the positive terminal. That is the reason this injection layer injects electrons towards the emitter terminal. So that is all about the how the current direction and how the current starts flowing through this particular IGBT, and that is the working of the IGBT. Only basic difference between power MOSFET and IGBT is this bottommost layer, the N plus layer will be replaced with P plus layer. And now structure of IGBT, as I have already explained, except N plus layer, the bottommost layer is replaced with P plus layer, and this is called injection layer, above which drift region determines the reverse blocking capability of IGBT. And when no amount of gate is applied, in that case current will not be flow, and when gate to emitter is voltage is applied, in that case the IGBT is turned on and then current starts flowing. And now coming to the transfer characteristics, this is a graph, collector current versus gate to emitter voltage. The moment when gate to emitter voltage is applied, in that case the current starts conducting. Once the gate to emitter threshold voltage is reached, only then current starts conducting. Once the gate to threshold voltage is reached, in that case, whatever the reverse bias depletion layer which is present, it starts breaking, and then current starts conducting through the device. And this is the collector to emitter voltage which is kept constant during the operation. And then we have output characteristics. output characteristics of IGBT, and this is the graph IC, collector current versus collector to emitter voltage. Keeping this gate to emitter voltage, the moment when gate to emitter voltage is applied, in that case, see, when gate to emitter voltage is 0, in that case the device will be in the off condition and there is no current flow through the device, and we call this condition as cutoff region. And during cutoff region, the device IGBT will be operating as an off switch. And once the gate emitter voltage is applied, and in that case the current starts increasing and it almost becomes constant. And here if you see, VGE5 is greater when compared to that of VGE4, is greater when compared to that of VGE1. And as the gate to emitter voltage is increased, in that case collector current increases and it almost becomes constant at a particular point, and that we call it as active region. And this active region is especially designed for transistor to operate as in the amplification mode. The transistor to operate in the amplification mode, and that we usually don't use in power electronics. Mostly will be going for cutoff region or otherwise saturation region. The transistor power electronic applications finds only cutoff region as well as saturation region. Either it will be operated as an on switch or otherwise off switch. We basically need a switching applications in power electronics. We don't go for amplification applications. Usually electronics people will be finding the applications of amplification mode. So we don't usually go for active region in power electronics applications. So here in saturation region, the transistor will be acting as an on switch. So when the current is increased beyond certain value, so it goes from active region to that of the saturation region, and there it will be acting as an on switch. And in the coming up lecture, we will be going for ZTO. Thank you.